Good afternoon. My name is Carlos Salcedo, and this is my final project assignment for ADTA 5550 for Professor Wynn. So to begin, I just want to give a brief overview with the table of contents for this presentation. The first part is going to be the introduction. Here, I'm just going to give an overview of the assignment. The project will be covering all the material we have learned over the course of the semester. For the main portion of this project, we'll be creating a model, training it, and examining the results for the CFAR-10 dataset provided to us on Canvas. And upon completion, we should be able to see the accuracy of our model to predict/assess the images, as well as be able to compare the results of the project to the one we did previously in assignment 4 with the MNIST dataset. For part 2, we're going to be going over the dataset that we were allowed to get off of the internet that has to be public domain, and we're going to discuss it regarding its ability to be processed using one of the same models that we're using right now. Part 3 is the actual building, training, and testing of the CNN model using the CFAR-10 dataset that we were provided with. Part 4 is going to be comparing the model that we built in this project to the model that we built back in assignment 4 using the MNIST dataset. And we're just going to be comparing just kind of the data used as well as the actual accuracy of the both models. And then for part 5, we're just going to talk about the different aspects that we can improve and on using the model, as well as what kind of effects these changes will have on the model itself. For part 1, this is going to be the data set of images or audio files that we were assigned to get on the internet that are public domain. The following data consists of a total of 44,406 fruit images, which can be divided into 15 different fruit categories, each captured with clear backgrounds and resolution of 320 by 258 pixels. There's 15 categories of actual fruit, but those 15 categories are further broken down into subcategories for different variations of the fruits, such as Granny Smith apples and red apples, green apples. Those are just a couple examples. The information, this kind of information can be applied to real world applications and actual neural networks, such as in the case of um, produce producers as well as superstores such as Walmart and Albertsons, Kroger's, those kind of companies. Um, they are actually using these kind of applications in order to check what kind of inventory they have and to make that process more autonomous, such as having people go in and no longer needing to go one by one on each one of the fruits. They're able to identify by just scanning using the barcode and double checking with the actual products, and by identifying with these neural networks they can cut time down from having to manually do that kind of process. As continuation, this is just kind of have the actual information is placed in the data file. So from right here, it has the main fruit category. So in this case, there was apple A, B, and C, where each one of them are different variations, and it shows how many total of those different type of variations they are, and it has each one of the different variation photos in that same column or row. I'm sorry. Um, it's pretty neatly contained, so you'd be able to clearly define what type of fruits are where. So for part 2, we're going to actually obtain the CFAR-10 dataset. The first step is to download the CFAR-10 dataset from Canvas. We have the URL listed right here, and it'll take you to this page right here on a Google Docs where you can download the information. There's actually a download button on the top right that allows you to download that to your locally hosted machine. After you download the files, you're going to go into your VM instance on Google Cloud Console, and you're going to go ahead and double check that that is indeed started. This is important because you need that to be running in order to connect to the SSH where you're going to actually do the uploading. To piggyback off of what I was saying in that last slide, we're going to connect after we start the instance of our VM. We're going to connect to the SSH, which is right here on the VM. And we're going to go ahead and click on that gear icon on the top right of the console once it pops up. So this little box right here, this is the actual console that pops up once you press on the button. And you're just going to go over to the upload file where it's going to let you choose your locally hosted image and your files. I'm sorry. After you upload all the images, it's important to realize that this is going to put them automatically up by default in your home directory for that VM instance. So the next thing to do is to move them over to your Jupyter Notebook. To do that, first you actually need to create a directory within that Jupyter Notebook to have all that data in one centralized place. So we're going to go ahead and use the mkdir command, and then we're going to name it this folder, which is cfar_10_data. And after we create that data, we're just going to double check that it's there by going into that data folder by using the command cd, which stands for change directory, and we're going to go into that folder. Here it kind of went through that process, and on this first image is just showing the creation of it. After you confirm that you have created that folder, you're going to go ahead and copy the information. So to do this, you can either use the cd space dot command, which will take you back one level on your directories. I went ahead and did that twice, so I went back to my home directory, which is where the files are uploaded manually and automatically. And from there, I can go ahead and use the copy function, and I went ahead and used the copy on all the folder files that I brought in, which is the data batch 1, 2, 3, 4, 5, the batches.meta and test batch. And then I redirected it to within the Jupyter Notebook to that cfar_10_data folder. That's going to be pivotal because if the information is not within that folder, then the code that we were supplied with will not work as it needs those files to be referenced. And on the first line of code, I believe it has a standard file directory to find those files, which it will not work if they're not placed in that Jupyter Notebook on the first level. So for part 3 of the project, we're going to actually build, train, and test the CNN on the CFAR10 dataset. Right here, this is just an overview of the actual design of the CNN model. It's going to start off with this image of the fish is going to be the actual input that we're going to be throwing into the model. This right here is kind of the convolution model where it really starts mapping everything out from the original input. And the max pooling part is a part that condenses the convolution part and kind of summarizes it so that it won't be as big of a file to really take as much time processing as it really should. After it's done being mapped in these two processes, it goes through a series of fully connected layers where it then kind of uses the different mapped points as reference points. And from there, it goes through as many fully connected layers as you want. And it then is able to identify which one of the categories or labels that you defined earlier it most closely relates to. To go a little bit more in depth, I have my project up for my coding. I'm just going to kind of go through this pretty quickly just to give a good idea of what I was doing. So this first part is just the standard file path for the actual information. That's why it was so important that we upload the photo correctly the images and the files correctly, because this right here is just referencing that one data file, and we have to make sure those files were populated in there. That's where that batch 1, 2, 3, 4, 5, and the other batch test batch files were all necessary. This part right here in the load data, all of this is really just setting up the data frame for the data and kind of giving everything a little bit more defined portion in this, such as this part right here. It's labeling, it's creating a variable, and it's each one of those variables is one of the data files that we brought in, the data batch 1, 2, 3, 4, 5 test batch. And if you notice here, we have 7 different variables in this all data, and we have 7 different files that we brought in. So each one of these right here in this array correlate to the files that we brought in here. So we're going to keep on moving along and running these. This is just setting up a simple data frame for it. This batch meta part right here, what this is doing is it's just showing the labels and the different type of categories that we have in our batch files. This is what's going to be used to really distinguish what is going to be what we're trying to classify for. So we have images of automobiles, birds, cats, deers, dogs, frogs, etc., etc. And this just kind of give a brief overview of those categories. These keys, the data batch 1 keys, this is just giving the actual titles in each one of those rows. So these batch labels are something that we assign to, and so you would basically be just seeing these as columns in that file that we brought in with the actual data and the actual file names. So this is just kind of giving you those headers for those columns. Down here on the display server images, this is more of an EDA process. It's just kind of grabbing some of the data, such as this one, it's grabbing the B data column from that data batch 1 file. And it's really just kind of to give you an idea of the information that you're bringing in. So a good example is like in this one right here, it's telling it to plot and show what's in that, what's hold inside that 0 index in X, which we define X as that data batch 1. So it's going to show that first image, and it appears to be a frog. It's a little bit pixelated just due to the fact that it's right, kind of right here. It's not great, but we go down here and we're using that same function, but now we're using the one in the what would end up being the second index spot, which is 1, and it's a picture of a car this time. So these are just really nothing more than just to give you a good idea of what kind of information is within those files that you're bringing in. This is just standard encoding labels. And this part is also part of that coding file that we received. This is just giving basic, setting up the class, which is in that CFR helper group. We're going to need that later on whenever we're going to actually train and test our model. But for now, all that's important is this is all setting up all the data and kind of getting the mapping ready. For here, this is just kind of ties into what we were doing here with it setting up those classes. So it's setting that up the CFR helper, which we defined up here as the class, and we're just giving it a quick reference name, which is going to be the CH. And the same goes right here. These are just going to be used to quickly reference those, so we created variables for them. Now down here is whenever we start actually creating and building the model. This information right here is very similar to what we did in assignment 4, we're defining the initial weights, the initial bias, and the first convolution layer. These right here are just really loosely defined. These could be anything you want it to be. For the for my easier understanding, I just had them as single characters just to make it easier on myself. Max pool is what we saw on the actual slideshow. That's going to be the condensing of the actual mapping. So that's what we have going on here on this field right here. And then this is just kind of running. Oh, I'm sorry, I didn't even run this part. Let me run these. This is just kind of reiterated up what we have right here. I needed just to redefine that. But these are just also just giving that convolutional layer and the full layer just kind of some definition by giving it a standard shape as well as setting its weights and biases. Now on phase one, I'm going to use the import function to bring in the TensorFlow package. It's essential that we do this because if we don't bring in that package, all these functions that have the TF in front of it aren't going to be able to function since it references those packages directly. After we run the import function, we're going to get these two placeholders. The first one of the placeholders is going to be for the inputs. So this is giving it the shape. Right here we have the batch size, height, weight, and depth of it. So this is just giving the inputs definition, well, not definition, a placeholder. And the second one is actually for the outputs. So that's what these two are referencing right there. This is just a do nothing, do not reshape. Data is already in good shape to be fed into this first convolution layer. The information we already had was actually set up, so we don't have to do anything, just like it says right there. Here, we're going to actually set up before the convolutional layer and full layer, we were just kind of defining them, but now we're going to actually create the actual layer. The first part of it is we're giving it the shape of all the convolution information that we're going to have. So this is going to serve as that first convolution layer right here. So we have the shape and the convolutional pool, which every single one of the convolutions needs a convolutional pool associated with it. So the convolution pool is in its mapped original form, and the pool is just the condensed version. And for the sake of this one, we're actually going to create two convolutional layers. So for this one, the same principle with that one, we're just going to create that convolution 2. And we're going to tie it back into that first convolution layer that we created. And then we're going to go ahead and pull it in, and we're going to have it aggregate both the convolution 1 and 2. After we're done creating the layers, we're going to go ahead and reshape the second convolution layer, because that's going to be what's feeding into the more inner layers, which is essentially going to feed into the output. And these right here, this is just helping out with the dropout outputs. We need those in case data isn't going to be used. We need to have it in the proper format so that we can still reference it. So those dropout functions are indeed essential. We go ahead and then use the cross entropy mean. We're going to need that for later on on the model, and as well as the optimizer, CNN trainer, and vars initializer. These are all just variables that we're going to need in the actual model portion, but for right now, it's not too significant. And that brings us actually down to the train and test of the CNN model. Now, right here, it's very similar to what we did in assignment 4 as well. We have our session getting created, the very first thing, and then we have our initializer, which we set up earlier. These are all just variables that tie into that session function. So this first important part is going to be the 5,000. This is going to be the steps it takes. So this is saying I want to make this run 5,000 steps, and each one of the batches is going to contain 100. So this is going to be the batch size, and this is the steps, and that's what's really going to be important. All these other variables right here, they're just kind of helping out, just define the model. CNN trainer is what we defined earlier, and so is the feed dictionary. And right here, we're just kind of seeing what we're going to bring in, which is the X batch at the 0 index. And then at the very end, we're going to go ahead and print the results of the accuracy. So if we go ahead and run this, excuse it, I ran it earlier, so it should be, oh, you know what, I might have not got through. I'm going to go ahead and run all these real quickly because I believe I might have skipped one whenever I went ahead and started clicking these. That's the kind of tricky part. You want to make sure that you get every single one of these blocks of code and you run them, because if you don't, you're going to be missing very important blocks of code, which one block is very significant in all these. So I'm just going through, rechecking. I ran all of them, and now it is properly running. So we see down here on the on step, that's the 0, and you can see a low accuracy level as it really hasn't gotten information in it. And then it drops down to the 100 step, and now you start seeing it go slowly and gradually going more higher. We can see the results later, but I just wanted to show that as an overview. And back to the PowerPoint, once I was finished running this, it showed that after 5,000 steps for the 100 step batch process, which we defined earlier and is what the code that you saw earlier, we ended up with a 69.42% accuracy for the model. It's well above 50%, which makes it somewhat reliable. And down here, you can actually see at what steps each accuracy level is. So that will end up being our final product. Comparing both convolutional neural networks performance, on the left-hand side here in the blue, we'll see that we have the model that we created in assignment 4, which is the MNIST dataset model. After building, training, and running the model, we ended up getting an accuracy of 99.12%. On the right-hand side, we have the CFAR-10 results of the model. That is the model we created in this project, and we ended up having an accuracy of 69.42%. A big reason for this big gap in the accuracy is indeed the input information that is being fed into these models. On the left-hand side, for the MNIST data, you can see that there's very little variation between the images, and the lack of depth in these images, as well as the fact that they are two-dimensional images, really influence it in the sense that it's really easy to map these kind of images. The only colors that are really present in these are the colors white, gray, and black. So it doesn't really make it too complex since they're kind of rasterized images that are just static. On the other hand, the CFAR-10 data, we have images such as planes, we have images for different animals, and the thing is, the background isn't consistent like it is in the MNIST data. So due to this, it's harder for it to classify since all those different images, like these planes, all these in the front first row are all planes, but the background is different in each one of them. So the actual mapping of these is going to come out to be a little bit harder due to the sense that it's going to have a harder time identifying it, since all of these are also showing different poses, have different color schemes, have different angles, as well as their shadows. So that's the reason why it's lower at a lower accuracy than the MNIST data. But Even though it is at 69.42%, that is still relatively accurate, as we consider anything that's above 50% justifiable. For part 5, in order to improve the convolutional neural network performance, I listed a couple of ways that we could achieve that. Um, One of the steps, which is the simplest way, is to increase the number of steps in order to get more training. You can also do the vice versa of this, which is decrease steps, but typically that will lead to lower accuracy levels, as the lower amount of training you have, the less actual sample sizes you have. This doesn't always hold true, however, because sometimes you can have more bias in your data. So it all really depends. So that's why there's not a really set stone and way to really get your accuracy up or low. It's really just trial and error. Another idea is to increase batch size. You could keep on increasing that or decreasing the batch size to have bigger or lower quantities at a time whenever you're testing this information. And another part is adding and removing layers. For our build this time, I ended up building 2 convolutional layers, but I could very much just do one or add as many as 10, 12, 30, as many as you really want. So it really all just comes down to you whenever you want to run this. But for the sake of mine, what I ended up doing was going back in my project. And on my project, I actually just switched out this 5,000 to 10,000, and I left my batch file as it is. And whenever I ended up finishing running that, I got a accuracy decrease of 0.44%. And that was in total, I ended up with a 68.98% accuracy, which really differs from what I had originally. But it's a slight change, but it just comes to show you that even if you substantially change the steps, you sometimes don't get as much of a decrease. Also, I tried this same process by using 3,000 steps, and I actually ended up with an accuracy decrease of 1.97%. So it just kind of comes to show that there's no real set stone way to increase or decrease your accuracy. It's really just up to playing with the different parameters. So I thought that was very interesting and insightful, because whenever you're working with these kind of models, um, it's there's quite a few things that you can do to improve them. But just to reiterate, in my scenario, I just ended up changing the number of steps, and that's how I got my final product. This concludes my presentation, and I just want to say thank you for watching the video, and it's been a pleasure working alongside everyone in my class, and thank you very much, Professor, for all the help in the class. I wish everyone good luck, and hope I'm wishing the best for everyone. Thank you.